Good afternoon. You're getting a second video for section 2.3 because I completely forgot that there was a second half of this lecture. So that's on me. I'm sorry. I'll definitely, if you guys need, I'll extend the homework for 2.3 so that you guys have time to deal with this. But we're still on section 2.3, techniques for computing limits. And I'm going to put this in the week 1 category instead of the week 2 category, just because it was supposed to be with last week's content. So let's get started. So the big concept that we're working with today is that there's sometimes a problem with just going in and plugging in A. And we saw that when we had our polynomial definition. It was P of A over Q of A is totally fine if our denominator is not equal to 0. So let's work with this example. Evaluate the limit as x approaches 2 of x squared minus 6x plus 8 divided by x squared minus 4. And we can see pretty easily from computation that if we just plug in 2, we're not going to be able to do something with that. If we just plug in 2, we're not going to be able to do anything with it. But if we draw the graph, we can also see that we've got just an open hole there. We've got a section that's undefined at 2. So there better be something that we can do instead. So what we can do is we can actually factor our polynomial on the top and factor our polynomial on the bottom. So this looks like we have x minus 2 times x minus 4 on top and x minus 2, x plus 2 on the bottom. We cancel out our x minus 2 terms. We're left with x minus 4 over x minus 2. And here, when we plug into, oh, sorry, this should be a plus. Here, when we plug into, we won't get a point on the graph that's not defined. Instead, so now let's plug in A. We get 2 minus 4 over 2 plus 2. 2 minus 4 is negative 2. 2 plus 2 is 4. We're left with negative 1/2. And when we look at our graph, we can see that that's exactly where our limit from the right and left approach. So we can still find the limit even if our graph is undefined at x equals 2. So that's one technique. You can always factor polynomials and see if anything cancels out. The next technique is a little bit more involved and it's a lot less intuitive, but I want to show you it because I want to show you guys that you can still do things even if things get complicated. There's still stuff that you can do. So let's look at another question where we have a problem with just plugging in the value A. And the problem occurs when we go to plug in 1. We get a 1 minus 1 on the denominator. That turns into a 0. We've got a problem there. So what can we do? Well, I'm going to conjecture that square root x minus 1 times x minus 1, or divided by x minus 1, times the number 1 is still equal to root x minus 1 over x minus 1. And if you believe that, then you might also believe that we can let 1 be any thing that we want. So I'm going to turn it into x root x plus 1 over root x plus 1. And hopefully you believe that root x plus 1 over itself is equal to the value 1. So with that in mind, I'm going to take root x minus 1 over x minus 1, multiply it by its conjugate, which is x plus root x plus 1 over root x plus 1. And I'm going to get out of this x plus root x minus root x minus 1 over x minus 1 times root x plus 1. Now our root x terms are going to cancel out, and we're going to be left with an x minus 1 on the top, an x minus 1 on the bottom, and a root x plus 1 on the bottom. Well, our x plus 1 term and our x minus 1 and our x minus 1 terms are going to cancel. So really, we're left with 1 over root x plus 1 as what we're evaluating the limit of. So now when we go to evaluate this limit, I'm going to scoot this over. We have no problem just plugging in 1. So we go and we plug in 1. It's going to be 1 over root 1 plus 1. We know the square root of 1 is just the value 1. So we're left with 1 over 1 plus 1, which is equal to 1 over 2. And if we look at the graph of this function, we'll find that it's the exact same. So even though this was a little more complicated, a little bit more involved, there's still things you can do that makes this pretty manageable. And the goal is always to take something complicated. Maybe it gets a little more complicated, but the goal is to make it into something simple, something where you can just plug and chug. So now that we've talked about plugging and chugging, let's talk about what goes on with the squeeze theorem. And this is going to be a really powerful tool. So the squeeze theorem is as follows. Assume that functions f, g, and h satisfy f of x is always less than or equal to g of x is always less than or equal to h of x for all values of x near a point A, except possibly at A. We might not know what goes on in A. If the limit as x approaches A of f of x is equal to the limit as x approaches A of h of x equals some value L, then the limit as x approaches A of g of x equals L. And this might sound like a bunch of nonsense, and for me, I really find it useful to look at some diagrams. So let's start by looking at some diagrams. The first one we're going to look at is this big boy right here. And the very first function, let's see, y equals x squared, y equals negative x squared, and in black we've got y equals x squared times sine of 1 over x. So it might not be clear to see, but to me, I've been working with this for a while. If we try and take the limit as we approach 0, we're going to run into some problems. First of all, if we just plug in 0, we get 0 squared times sine of 1 over 0. We already know that we've broken a rule because we've got 1 over 0. We've got a 0 in the denominator. But we don't have any tricks yet for what to do to make this simple, right? We can't factor, we can't use a conjugate to turn sine of 1 over 0 into something that's not sine of 1 over 0. So we need to use something else. So in black, I've got drawn y equals x squared times sine of 1 over x. And we can see that something is certainly going on around 0. We just don't know what. So we're going to use the squeeze theorem instead. And the squeeze theorem says that as long as I've got a function f of x, and everywhere it's less than or equal to a function g of x, and everywhere g of x is less than or equal to a function h of x, well, if we know the limit of h of x and f of x and they equal the same thing, then we've forced our limit of g of x to be that very same thing. So we know that f of x and h of x both obey those laws that we said in the first part. So now it's just a matter of finding the limit. Well, the limit of the function negative x squared as x approaches 0 is 0. So limit x approaches 0 of f of x equals 0. And now we just need to check what our limit is for the top one. So the limit as x approaches 0 of f of x, well, we can just plug this in. We know it to be 0. So it's 0. So our limits for the bottom function and the top function of our squeeze theorem both equal the same thing. So because of the squeeze theorem, we know that the limit as x approaches 0 of our function g of x better equal 0. It better equal that same value. So maybe this was a little bit of a contrived example because I gave you the two functions to start with, but let's see what we can do with some more. So let's move on for some more examples. So in this one, we're going to use the squeeze theorem to find the following limits. And we're interested in something that's going to be a little bit obvious. So f of x equals sine of x. Well, we could just plug in 0, and we know that sine of 0 is 0, but can we prove that the squeeze theorem works? And the answer is yes. So our f of x function is going to be the negative absolute value of x function, and we know that as we approach 0, the limit equals 0. Our h of x function is going to be just the absolute value function, and we know that as we approach 0, the limit equals 0. So we've squeezed our sine function in between two other functions whose limit as x approaches 0 equals 0. So the limit as sine approaches 0, or as x approaches 0 of sine of x better equals 0. So hopefully that makes sense. And you can choose, it might be in a homework problem, it might be up to you to pick these functions. But good functions to pick are absolute value functions, negative absolute value functions, the square function, the negative square function, things like that are always good to pick. Or in this next case, we're going to see something that might not be so obvious, but is also a good one to pick. So in this next one, we're interested in what's the limit of the function f of x where f of x equals cosine of x and x approaches 0. Well, again, we can just plug in 0 and we know that the value is 1, or we can use the squeeze theorem and we know that cosine, just cosine of x, is never going to exceed the value 1. So why not make our upper function h of x equals 1? And why not use f of x as 1 minus x, or 1 minus the absolute value of x? And then we get that h of x as x approaches 0 is 1. The limit as x approaches 0 of f of x is also equal to 1, because we can just plug in 0 for x, and then we just get the value 1. So the limit of f of x, our cosine of x, as x approaches 0, that better also equal 1. And we did that using the squeeze theorem. So because of the squeeze theorem. So hopefully that's a nice little introduction to the squeeze theorem. We won't really use it outside of being introduced to it, but that's okay. There's definitely going to be some homework problems about it. So that's it. I look forward to seeing you guys in video 2.4.